Optical multiplexing is the topic of this lecture. In previous lectures, we have discussed about optical channel, optical link, and then how the data rate, high data rate, increased bandwidth are the important factors in transmission of signal over an optical link or optical channel. We can use a full duplex system in transmitting the signal where the two separate cables can be used for transmitting and receiving the signal at the same time. But multiplexing is a scheme which is very popularly used in optical communication system, where as in any multiplexing scheme, a number of signals are transmitted through a single channel. A number of messages, number of signals can be transmitted through a single path called as multiplexing. So in optical multiplexing, we will focus on exclusively the multiplexing schemes which are used in context with optical communication system. So to begin with, this is what we have discussed in previous lecture about fiber link that consists of transmitter, receiver, and series of fiber amplifiers. The optical link connects transmitter and receiver. End-to-end connection is made by combining transmitter, receiver, and the fiber amplifiers. Dispersion and other losses are the important factors that affect the signal quality, and the signal strength gets degraded. And this is why we use fiber amplifiers after certain distance, certain gap in the optical link. The aim in any fiber optic link is always to get high data rate, very high data rate with minimum loss, minimum fiber loss. So this is about fiber link. In the same link, the scheme called multiplexing can be used, which allows more and more number of signals to be transmitted simultaneously. So as we know that, you can see here the multiplexing is an expansion of existing fiber network engineering. The multiplexing is very important to expand the fiber network capabilities to get enhanced data rate and high bandwidth communication system. The multiplexing techniques are used in increasing, let me choose a pointer. The multiplexing techniques are used in increasing the data carrying capacity of a single optical fiber. The multiplexing techniques are used in increasing the data carrying capacity. If you do not use multiplexing, the data carrying capacity will not be large, but if you use multiplexing, it enhances that capacity. There are popular multiplexing schemes used in optical communication called as optical multiplexing methods that includes wavelength division multiplexing, also known as WDM, very popularly known as WDM, wavelength division multiplexing. Next is optical time division multiplexing, that is OTDM, optical time division multiplexing, OTDM, and space division multiplexing, SDM, space division multiplexing, subcarrier division multiplexing, are the different names, even though the TDM is also used. See here, optical time division multiplexing is TDM actually, but used in optical link, used in optical communication called as optical TDM. So WDM, optical TDM, SDM, and subcarrier division multiplexing, which also can be called as one of the SDM types, are the popular methods for multiplexing the signal in optical communication system. Optical transmission uses pulses of light to transmit information, and then light is converted to electromagnetic carrier wave, which is modulated to carry information as the light propagates from one end to other. This is the general principle, fundamental principle used in optical communication system. The light pulses, which are converted into electromagnetic carrier, the carrier is used to modulate, or rather carrier is modulated by the message signal, and then that propagates in the form of light, and then back at the receiver we convert it back into the electrical signal. So the development of optical fiber has really created revolution. It has been, it has revolutionized the telecommunication industry by providing very high data rate and increased number of subscribers that can be accommodated in a bandwidth. So the optical fiber is or has been used to develop new high-speed communication system which transmit information as light pulses. The information is transmitted in the form of light pulses, and using multiplexers and demultiplexers or multiplexing scheme, high-speed data communication is achieved. When we discuss about multiplexing, demultiplexing automatically comes. Multiplexing is used in the transmission side. So in the receiving end, we have to use demultiplexing. Because in multiplexing, multiple signals have been, in one way we can say, merged together. And a scheme has been made that a number of signals are communicating simultaneously. To separate all the different signals, there is a scheme which is required at receiving end called as demultiplexing. Multiplexer combines multiple analog or digital signals based on the type of multiplexing scheme. So the number of either analog or digital signals are combined into a single line of transmission. The line of transmission is single, but there are multiple signals which are combined on the basis of some factor, some parameter, which we'll discuss in different multiplexing schemes. Because it varies when we talk about WDM, wavelength division multiplexing. So the division will be made on the basis of wavelength. When it is time division multiplexing, all the messages, the different signals will have been or will be allocated to different time slots. So there will be a sampling time, and the sampling time will be divided into a number of message slots. In that particular slot, message will be allowed to be transmitted. So therefore, on the basis of some factor or parameter, the division is made. At the receiving end, demultiplexer is used. It performs the reverse operation. Multiplexing enhances efficiency of bandwidth. It improves the efficiency of bandwidth. How? It enhances the efficiency of bandwidth because if a channel bandwidth, or in a given channel bandwidth, if there is only one signal traveling, the utilization of bandwidth is not very good, because if more number of signals could really be accommodated in the same bandwidth, that could provide high speed communication, large data rate can be communicated. But instead of that, we are only communicating one signal. So the data rate is less, the speed is less. So therefore, the utilization is increased. It means the efficiency of the bandwidth, efficiency of utilization of bandwidth is enhanced, is increased by using the multiplexing. This is one scheme where we can see that There is a common port where the port connects other links. There is upgrade link where some more further links can be connected. And these are the IO devices, IO ports where a number of IO devices can be connected. And these are the filters which we will discuss about, that what these filters are used in different multiplexing scheme. So this is one scheme where that the number of links in this manner can be connected one by one, and then that each link is providing a multiplexed signal. So therefore, you see that the different colors means different wavelength, because we know that color of light is characterized by certain value of wavelength. So all these different colors means different wavelength. So different signals are coming together, and through different IO port, we can receive a different signal. Different color of signal means different wavelength of the signal. So this is one scheme which is highlighted as the multiplexing. Each IO port will be used for single wavelength. That has been shown here also. Like this IO port is for red color, the next IO port is for green color, the next is blue, and another one is yellow color. Optical multiplexer and demultiplexer, which are written as MUX and DMUX, are actually passive optical filter systems which are arranged to process specific wavelength in and out of optical filter. And this is why these multiplexers are called as passive, filters, because a particular wavelength will be chosen. All wavelengths have been combined. Now, while separating the signal, we are using different filters, right, in the output IO port area. So this is why we can call them as a filters, which are used to select certain wavelength and used to attenuate other wavelength. On the basis of certain port or using certain port, we can extract a particular wavelength. In the similar manner, other ports will be designed to recover the different wavelengths separately. So the process of filtering this wavelength can be performed using prism. There are different devices which are used: thin film filter, TFF, right? Dichroic filters are interference filters. There are different filters which are passive filters used for this purpose to extract the different wavelength. The filtering materials are used to selectively reflect a single wavelength of light but pass all others transparently. So the purpose is to select one wavelength and not to select other wavelength. Each filter is tuned for a specific wavelength. Each filter is here that all these, see, whenever we are trying to separate the signal which is coming from the multiplexed output, we are using filter. Wherever there is a port, there is a filter. And this is why each filter is tuned at specific wavelength. And that signal corresponding to that particular wavelength is delivered through an IO port. This is one scheme highlighting the MUX and DMUX. You look at here that in both the areas that input output lines are there. Suppose we receive the signal at the receiving end. Actually, the multiplexer consists of combiner, tap count, coupler, filters, splitter, optical fiber. You can see there is a tap coupler, there is a tap coupler, where add and drop operation can be performed. Then splitters, combiners, because see, when we are transmitting, they will be combined. When we are receiving, they will be received. I mean, they will be combined, they will be splitted. One message signal is coming, that will get splitted, and when we are transmitting, all the different signals are combined together. They are added through the tap counter, and then they can be muxed. And while demultiplexing, look at here, after demultiplexing using a tap counter, so here the operation is dropping. Adding is used when we are combining, dropping is used when we are splitting. So there are operations, tap counters for adding and dropping. Adding is used at the transmitting end, whereas the dropping is used at the receiving end. So these are the different wavelengths. You can see here wavelength blocker, that one of the filter will be corresponding to one particular wavelength. But ultimately all signals have been merged together, and how the signals have been merged together on the basis of certain value of wavelength. So it's a scheme called as wavelength, division multiplexing. So as I told you that there are major techniques called as OTDM, that optical TDM, optical time division multiplexing, WDM, which is of again two types, CWDM, DWDM, where C stands for coarse and D stands for dense, right? Coarse and dense. And CDM, code division multiplexing, that is also used in the optical link or optical communication system. So we will separately discuss all the multiplexing schemes. This is the lecture where we are discussing an overview of multiplexing scheme. So in OTDM, separating wavelengths in time, because in optical signal, every signal is in the form of light. So light is characterized by wavelength. So all the wavelengths are to be separated in terms of some time slot called as optical TDM. In any TDM, time slots are allotted to different messages, different slots of signals. And all those slots are corresponding to certain wavelengths. So wavelengths have been separated on the basis of or have been allocated different time slots. WDM, each channel is assigned a unique carrier frequency and channel spacing of about 50 Hertz. This includes coarse WDM and dense WDM. What is the basic difference between the two? In coarse WDM, it is characterized by wider channel spacing, and in DWDM, narrower channel spacing. The spacing between the two separation between the two, you can say slots or wavelengths, will be wider in coarse one, wherein dense one, as its name suggests, dense. So the separation will be much lesser as compared to the coarse DWDM. What are the pros and cons of each of these methods? We will discuss separately. In CDM, it is used in microwave transmission. Spectrum of each wavelength is assigned a unique spreading code. As its name suggests, code division multiplexing. Code division multiplexing. So, a unique code is allocated for each particular wavelength. Like in TDM, different time slots. Similarly, each wavelength is assigned a particular code. So on the basis of code, then multiplexing happens. We call it as code division multiplexing. The channels overlay both in time and frequency domain, but the code guide each wavelength. There will be overlapping in time and frequency, but the code will be always unique for each particular wavelength. That's what is called as CDM. Then multiplexing techniques are used to increase optical transmission system capacity over a fixed bandwidth. They are used to increase the transmission capacity over a fixed bandwidth. We are not changing the bandwidth, but we are enhancing the capacity of the channel. Enhancing the capacity of channel means we are improving its utilization. We are improving its efficiency, usage efficiency. And this is why the capacity is improving, capacity is increasing, optical capacity. Otherwise, the channel bandwidth remains same, but in the same channel bandwidth, how much or how many more messages can be transmitted together? That's what is the scheme called as multiplexing. And therefore, the capacity, what is called as optical capacity, optical transmission capacity will be increased. WDM is one of the multiplexing techniques which increases bandwidth by multiplexing a variety of carrier signals into a single optical fiber by using different wavelengths. All different carriers will be modified or will be modulated by different wavelengths using a single optical fiber. Therefore, and then only it will be called as multiplexing scheme. It will be known as multiplexing scheme. Each signal a WDM wavelength is independent of any protocol or any speed. I mean, because when we transmit some information, there are protocols which are used in wireless or this network communication system, where in digital communication system, there will be certain rules and regulations for which or by which the exchange will take place, exchange of information will take place. But the signal corresponding to a particular wavelength will not have that much dependency on any protocol or the speed. WDM technology allows bidirectional communication simultaneously over a single optical fiber. That is the benefit, bidirectional. We can use some splitters in a number of places, but bidirectional communication WDM allows, right? Because what happens that the multiplexing has been done in such a manner that a particular wavelengths have been allotted different wavelength slots, and accordingly the transmission is happening. CWDM and DWDM, which are coarse and dense, which are based on same concept of multiple light wavelengths on a single fiber. In both the scheme, we will transmit more number of wavelengths, either it is CWDM or DWDM, but differ in the spacing of wavelength, as we have already noted that in DWDM, the spacing is less, whereas in CWDM, the spacing is large. So the CWDM and DWDM are differentiated, and the difference depends on a number of factors. The spacing is one of those factors, but there are other factors like number of channels that can be accommodated, the ability to amplify the multiplex signals, ability to amplify the number of channels, and the spacing are the factors which differ or which make the difference between CWDM and DWDM. This is one scheme called as, the typical block diagram for WDM. I think the block diagram is self-explanatory. You see here, it's a WDM transmitter. So the different signals having different wavelength. If you look at the lambda 1, lambda 2, lambda 3, lambda 4, and that too having different colors, are combined here, and they are all transmitted through a single channel, and they are separated here by using demux, and demultiplexer separates, and then we can deliver all those different signals to different ports separately. So this scheme is called as WDM, that is wavelength division multiplexing. Then comes, because this lecture is introductory lecture, so all the methods will be discussed briefly. As in WDM, you have seen that it multiplexes, it combines on the basis of wavelength. So in OTDM, as its name suggests, time division multiplexing. So this is the technique in which the multiplexing is applied, and at a number of low bit rate optical channels in time domain, and more number of low bit channels, low bit optical channels, that too in time domain can be multiplexed together in OTDM. Several low speed optical channels are multiplexed, low speed channels, more number of optical channels having low speed can be multiplexed together with a fixed electric clock period and increased transmission speed. Because the transmission speed will obviously increase, it's due to the fact that multiplexing allows more number of signals that to be communicated simultaneously. Each signal is transmitted over a single communication channel by dividing the time frame into slots, one slot for each message signal. This is very important in OTDM, in any TDM. So one time frame, which is, you can say, the part of sampling interval, sampling time. One time frame, that frame will be shared among a number of message signals. So suppose there are 100 message signals or 10 message signals. So that time frame will be divided into 10 equal parts, and each time slot will be allocated to one particular signal having a particular wavelength, lambda 1 or lambda 2 or lambda 3, whatever. And accordingly, all signals will have different allocation, and in different time slot, different signal will be traveling. But the sampling rate is so high that when we actually separate and deliver to different IO ports, the user cannot point out cannot make it that the signal was actually separated, combined together, combined and separated again. That difference cannot be made. So based on time, each low speed channel is allocated to a specific position in synchronized mode. Synchronization is very important. Synchronization in TDM is very important because if there is any difficulty in synchronization, if there is any delay in a particular time slot, a specific wavelength is supposed to travel, but there is delay means in the receiving end, we will understand that in a particular time slot, we are receiving actually the different wavelength, which we were not supposed to receive at that time, at that particular time slot. So that problem is, it creates synchronization problem. So synchronization is very important thing that has to be kept in mind while implementing OTDM. The multiplexer and demultiplexer are therefore timely synchronized. They are synchronized in time domain. Why in time domain? Because the division, the separation has been made in time slot. So that synchronization in time slot and in time domain has to be there. Okay, this is the scheme. I think for time slot, the different senders will be allocated different time slot. You can see here 1, 2, 3, n. So this 1, 2, 3, n are say 1. 1 is the message 1, 2 is the message 2, 3 is the message 2. But these are small blocks. The blocks are different part of the wavelength which is transmitted during a particular time slot. That is very important. And that will repeat. So you see here 1, 2, 3, 1, 2, 3. It will keep on repeating because there will be a commutator kind of device that will facilitate that after every interval, every certain interval or a specific time interval, a particular wavelength will be chosen, and in that time slot, the wavelength will be allowed to transmit, allowed to travel. So this is why the synchronization is very much needed. If there is poor synchronization in a particular time slot, the wavelength which are supposed to be delivered, rather other wavelength will be delivered, and the entire then delivery, entire sequence of the data will be disturbed. So there must be synchronization. The optical pulse width is shortened in order to multiplex more channels. Optical pulse width will be made small in order to multiplex more number of channels in a clock period. Because smaller is the duration, more will be the channels. Large will be the time duration, less will be the number of channels. In a particular time period, if we divide the time frame and the time frame is, is divided among a number of channels, the time slot is very less, so more number of channels can be accommodated. And we also need to, this smaller pulse width can reduce the crosstalk between the channels also because of more space left in the bit rate. So crosstalk problem, which is actually interference between the two adjacent signals, will also be allowed by this scheme. But the short pulse or small width pulse results in heavy dispersion as traveling distance increases. When the smallest duration pulse or very small duration pulses are sent, that may increase the dispersion, and when the dispersion is there, so it may feel like that it has traveled a long distance and there will be signal degradation due to dispersion. So the transform limited pulse, not the ordinary light pulse, but transform limited pulse and the dispersion slope compensation technique are the techniques which are used to reduce the dispersion effect in OTDM. Dispersion cannot be avoided, but the effect can be reduced by using either a transform limited pulse method or dispersion slope compensation. As its name suggests, the slope will be provided in a negative manner so that the dispersion introduced can be compensated. Now, these are some emerging technologies or emerging techniques, and then we will talk about applications, advantages and disadvantages. These are the emerging techniques which are used in all modern, application of optical communication. SDM, space division multiplexing, which utilizes the spatial dimension to simultaneously deliver different data streams by creating a parallel spatial channel. So in space division multiplexing, spatial domain division takes place. So in parallel way, the operation or multiplexing is performed, and we all know the benefit of parallel computing or parallel operation. So it's emerging, it's very much beneficial, which improves bit rate as well as the data rate as well as the speed. This technology is used in multiple input, multiple output, very popularly known as MIMO system, used in all wireless communication system. Most emerging and modern wireless communication system utilizes MIMO, multiple input, multiple output. The number of inputs is multiple, number of outputs is multiple, and we have to have that kind of communication. So MIMO system that incorporates at least two antennas at the transmitter and at least two antennas at the receiver. So at least 2 cross 2, that is number of input 2, number of output 2 in a MIMO system. But the number of inputs and outputs may be more than 2, where SDM is very important and beneficial in the MIMO kind of application. MIMO is already widely used in current coherent optical transmission system with polarization division multiplexing called as PDM or standard single mode fiber. It's already in use using multi-core and multi-mode fiber. It's not that the multiplexing schemes are used only for single mode, but they're used for multi-core, multi-mode fiber, long-haul transmission, distance and high speed, long-haul distance, transmission distance, high-speed data rate, and high-density SDM are the possible versions of the space division multiplexing scheme, multiplexing method. These are some applications, as we have discussed, that wherever in the application where the utilization of bandwidth we want very good, we want to accommodate more number of subscribers over the same bandwidth. So in a telecommunication, optical communication system where the high bit rate, high speed are expected or intended for common bandwidth. In those all applications, the multiplexing, optical multiplexing can be used. It reduces also cost of hardware. One multiplexing system can be used to transmit and multiple signals, combine and transmit multiple signals from one location to other location. So each wavelength can carry multiple signals using the same wavelength. The different signals can be carried. Optical switching of signal and telecommunication and other DSP operations is also used. So in digital signal processing also, this multiplexing scheme is used when the data comes and delivers in the form of light. The future next generation internet, and this has already started in the emerging applications, emerging internet based communication system where there is optical communication, optical cable, large fiber optic communication system is involved where we want high data rate over a certain bandwidth. These are some major advantages of the optical multiplexing. High data rate and throughput, I have already explained. The biggest benefit is high data rate because we allow more number of channels over bandwidth, so we get more data rate and throughput. High data rate is possible in optical communication in even Gbps or even in Tbps, but 1 Gbps can be obtained only on each wavelength. That's also possible because of multiplex. And the combination of different wavelength means more throughput in a single communication system. More throughput, more number of signals are there. So if it are there, so effectively you can say the amount of output, the quantum of output is more, and therefore throughput is also more. Low attenuation is not a big concern. So attenuation is low. Less propagation delay is not a big problem. More services offered because multiplexing itself is a name that more and more number of services, more and more number of signals intending to communicate different types of information can be communicated. So more number of signals, more services can be obtained by using multiplexing scheme. Low bit error rate is a important factor in any digital communication system where how many bits are actually erroneous, how many bits are actually received incorrectly. So that is not a big problem in again multiplexing. Rather, in multiplexing a scheme, a proper synchronization is there, then the bit rate, that is bit error rate, is minimum. There are some drawbacks associated with the multiplexing called as fiber output loss and dispersion. Signal is attenuated by fiber loss and distorted by fiber dispersion. So more and more number of regenerators are used. If there is fiber loss, more number of fiber amplifiers, fiber regenerators to compensate the dispersion, to compensate the loss will be the requirement. So that will put an extra cost to the system of optical communication. Next one is optical to electrical conversion overhead. Optical signals are converted into electrical using photodetectors, switched, converted back to optical. We know that optical signals are converted into electrical, electrical are converted into optical. So more and more number of such conversions are taking place. So these conversions introduce some unnecessary time delays because the conversions are being made by the optical, rather electronic devices, semiconductor devices, that will, those devices will cause some delay, and that delay is unnecessary. And because of that delay also, because the signals are passing, converting again and again through the different electronic circuits, so that would also be the reason for one of the reasons for the power loss also. So power loss, unnecessary time delay, loss, that is optical loss, and the dispersion are the major problems in the multiplexing scheme. So we can combine, or we can rather summarize here, optical multiplexing is an important method used that allows more and more number of signals to be transmitted over a single channel simultaneously. There are popular methods used as optical multiplexing techniques, and one of the methods called as WDM is the most popular. Wavelength division multiplexing. WDM, as its name suggests, the division, the separation is made on the basis of different wavelengths. So different signals will be corresponding to different wavelengths. WDM is of two types: CWDM, coarse WDM, and dense WDM. In dense WDM, separation between the two signals channels will be less. In the coarse WDM, separation between the two signals will be more. But the CWDM, DWDM, and all WDM techniques we will discuss separately in a separate subsequent lecture. The number of channels, the number of signals, the data rate, high or low, the spacing, are the factors which differentiate WDM, or which classify WDM in two parts, CWDM and BWDM. There is another method which we have introduced, is OTDM, called as optical time division multiplexing. Like other TDM, the signals are divided in different time slots, and different time slots means each time slot will correspond to a particular wavelength, and a time frame is chosen, and that time frame is divided into a number of time slots, in which in each time slot one wavelength will be allowed. So as a summary, we can say, like using multiplexing and digital communication in all digital signal processing, the multiplexing is equally beneficial, advantageous in optical communication system also, and therefore we use specific methods called as OTDM, WDM, SDM, as even the CDM is also used, code division multiplexing, as a popular methods for optical multiplexing, to multiplex more number of signals, to allow more number of signals over a single channel to achieve high data rate, high speed communication system over a specific value of bandwidth. So that's all for this lecture. Thank you.